Have you ever stopped to wonder how engineers figure out the insane forces on a curved airplane wing? Or how physicists can actually map out the electric field inside something like a battery? Well, if you have, you're in exactly the right place. Today, we're going on a journey, way beyond the flat, simple world of basic calculus. We're going to explore the amazing tools that let us measure, well, pretty much everything in our three-dimensional universe. Let's dive in.
So here's our game plan, our roadmap for this journey. We're going to start on solid ground, with stuff we probably already know. Then, we'll level up to tackle curved surfaces. After that, we'll dive deep into three-dimensional volumes. And finally, the best part, we'll connect all the dots to see how this all fits together into one beautiful, unified picture of calculus. All right, before we jump into the really mind-bending stuff, we've got to take a quick look back at the foundation. Let's start on familiar territory with the integral we all know and, hopefully love. Yeah, you remember this one from class, right? The classic integral, the go-to tool for finding the area under a curve. And look, it's a fantastic tool for one-dimensional problems. It's really the bedrock for everything we're going to get into today. But here's the thing. That simple tool, it kind of hits a wall when you step into the real world. I mean, the real world is messy, it's curved, so what do? How do you figure out the mass of a curved satellite dish? Or how could you possibly calculate the total amount of water flowing through a fishing net in the middle of a river? For problems like that, we're going to need to level up our calculus. So, to answer those very questions, we need to introduce our first new tool, the surface integral. This is where we say goodbye to the flat world and we really learn how to work with the curves and contours of 3D space.
To put it simply, a surface integral lets us add up some quantity, but over a surface that isn't flat. Just imagine taking that familiar double integral and stretching it, kind of like a sheet of spandex, to fit perfectly over any curved shape you can think of in 3D space.
Now here's where it gets really, really cool. This one mathematical tool, it actually has two totally different personalities, you could say. It all depends on the job you need it to do. It can either look at what's on the surface, or it can look at what's going through the surface. Let's break that down.
Okay, on the left, we've got a scalar field. That's just a fancy way of saying that at every single point on our surface, there's a number, like temperature or density. When we integrate this, we're adding up a quantity that lives on the surface. Think about finding the total mass of a curved piece of metal. But on the right, we've got a vector field. This is totally different. Now every point has both a magnitude and a direction. Think of wind or flowing water. Integrating this measures how much of that stuff is passing through our surface. And this idea has a crucial name, flux. So see the difference? One is about what's on the surface, the other is about what's going through it. Let's really focus on this idea of flux, because it's a huge deal. It's an incredibly powerful concept. It doesn't just tell you that, hey, water is flowing. No, it tells you exactly how many gallons per second are passing through that specific net. It actually quantifies the flow across a boundary, which makes it absolutely fundamental in physics and engineering.
And believe me, this isn't just theory. A perfect real-world example is Gauss's law. It's amazing. It uses a surface integral to show that the total electric flux pouring out of a closed surface, say a sphere, tells you with perfect precision how much electric charge is trapped inside. It's a cornerstone of how we understand electromagnetism.
Okay, so we've mastered surfaces. What's the next logical step? Well, let's go inside the shape. We're moving from 2D surfaces into full-blown three-dimensional volumes.
Now, as you can probably guess, a volume integral takes this whole idea of adding things up and just kicks it up into 3 dimensions. We're not just on a surface anymore, now we're calculating a total amount of something that's distributed throughout an entire 3D space.
The most intuitive way to get your head around this is with density and mass. Imagine you have some object where the density isn't the same everywhere. Maybe it's way denser in the core. The volume integral is the tool that lets you go in, add up the mass of every single tiny little cube inside, and get the total mass of the entire object. Okay, get ready for this because this is where it all clicks together. This is a real aha moment. We've talked about what happens on a surface, that's flux, and we've talked about what happens inside a volume. But what if those two things are deeply, fundamentally connected?
Just picture this. What if you could measure every little bit of stuff flowing out of a totally sealed container? I'm talking every bit of air, every drop of water, every bit of energy passing through its outer surface.
And what if that single measurement, taken only at the boundary, could tell you precisely what was creating or consuming that stuff deep inside the container?
Well, that very question leads us to one of the most elegant and powerful theorems in all of mathematics.
And here it is, the divergence theorem. This is the bridge. It says that the total flux flowing out of a closed surface is exactly equal to the volume integral of something called the divergence on the inside. So what's divergence? Just think of it as a little meter that tells you how much a field is spreading out or sourcing from any given point. So this theorem creates an incredible link. What happens on the boundary is perfectly described by what's happening at all the sources inside the volume.
So, we've explored integrals for lines, for surfaces, and for volumes. Now it's time to zoom out, pull back, and see how all of these amazing pieces fit together to form one single, elegant system for describing our world.
This table, it just lays it all out beautifully, doesn't it? You can see the progression. We start with a line integral in one dimension, which we often use to calculate the work done along a path. Then we move up a dimension, to the surface integral, to find mass on a surface or flux through it. And finally, we arrive at the volume integral in 3 dimensions for finding total mass or charge within a space. Each one is a step up, a new layer of power.
And here's the real takeaway, the big idea. These aren't just 3 separate random math tricks. No way. They are a single, coherent toolkit. You can almost think of it as a fundamental grammar for describing how things add up and how they flow in our physical world, from a simple 1D line all the way up to a complex 3D space. When you think about it, from the gravitational pull between planets to the way heat moves through a tiny computer chip, these integrals are the language we use to understand and engineer it all. It really makes you wonder, right? As we keep pushing the boundaries of math, what other invisible forces, what other hidden structures of our universe are we going to be able to map out next?